Let's go to the very beginning of what we learned. We started everything with u-substitution. Usually, u-substitution topic goes to the Calculus 1 class. U-sub, integration with u-sub. Usually, it's the very end of Calculus 1 class, but somehow in this school it did not fit. I don't know why. So that's the first topic of Calculus 2. U-sub, we did some detailed one and fast one. Different types of them. So you can practice as many things as you can. I solved all of these problems for you from the exam review. So your job is to recognize u-sub. That's like literally the first step is to recognize, is it u-sub, integration by parts, or anything else? So if you have ln x to the 4 over x dx, and then you feel stuck, you don't know what to do, you should always remember u-substitution is undoing chain rule. Undoes chain rule. And chain rule means there is a function that was differentiated from inside of another function. So using u-sub is convenient if one piece looks like derivative of another piece. Well, I see log and I see x. No connection, I don't see. But then I see carefully, it's log and 1 over x. Log and 1 over x have connections. So if I am writing it as ln x to the 4 times 1 over x dx, then it's visually clear that one of them can be u, and when you differentiate that one function, it gives you another function times scaled to a constant, that's how they say it, or scaled. So who knows? So should I choose ln to the 4 to be u? What do you think? No, let's just choose log to be u, right? Then it's going to be u to the 4. So usually p's inside goes to be as u. The thing is you can try anyway, and then if it doesn't work, try another way. That's kind of try and fail idea. If log is u, then 1 over x dx is du. Let's write down carefully the notation. Let u be ln x, then du is 1 over x dx. And this is what we're doing here. Using this notation, it becomes integral of u to the 4 du. It's perfect. Remember, u-substitution is a transformation, so you have to change limits of integration if you have any. So I'm going to do it in the next example. U to the 5 over 5 plus c. No, you have to go back unless it's a definite integral. Nobody knows what the u is, so you have ln x to the 5 over 5 plus c. The beauty of this problem that you can check if your answer is correct, you can just differentiate the answer, and it should give you whatever was inside of the integral. So technically speaking, if it's multiple choice, you can differentiate all functions and see which one is the correct one. But it would be nice if you actually know what you're doing. Does that make sense? Let's do one more with square roots and stuff you guys don't like. Integral from 0 to 10 x over the square root, and then there is 9 plus, oh, that one is actually too annoying. But it's fine. Let's do x squared. Yeah, dx. I changed it a little bit. So I don't see connection, but then I look carefully and I see 9 plus 4x squared. Derivative of that will be 8x. And I do have x somewhere else. So derivative of one thing gives you somehow another thing scaled. Scaled means times some kind of constant. So my guess is that everything inside of the square root should be u. If you choose everything to be u, you will have to deal with differentiating the square root, and that will be harder and might not help. U to the 1/2, or in this case minus 1/2, we can do that. But with other case you can try, it might not work. U-substitution, if u is 9 plus 4x, let me put it to blue. It's not that serious, so blue, not pink. Then Oh, 4 squared, thank you. du is 8x dx. We need x dx, and we just got 8x dx. So solve for x dx. I usually multiply by 8 and divide by 8. But I can see many people actually like the idea that I just need to solve for this piece. X from the second equation, x dx can be solved as 1/8 du divided by 8. Now we're going to be plugging the first equation. U is 9 plus 4x squared, goes to the inside of the square root. And then x dx is the numerator. Not done. We need to figure out 0 and 10. Let me remind you how to do that. When x, let me put it in blue, that is part of u-substitution. When x is 0, u was chosen to be 9 plus 4x squared. So now we have 0 squared instead of the x squared. So u becomes 9. When x was 10, u becomes 9 plus 4 times 10 squared, which is 400 plus 9, 409. The first one was A, the second one was B. This box is my u-substitution box. Integral becomes from 9 to 409, x dx in yellow. X dx in yellow, we found it as 1/8 du, then maybe kick out 1/8 outside. Du will go to the end, and I have 1 over square root of u du. Does this make sense? So did this look like a magic, or you got it? Can you do it on a test? That's not the answer yet, but can you do this on a test? This is the most important part. And there's a second important part, what to do with the boundaries. Do we go back or not? So let's do that. First of all, let's integrate 1 over 8 u. So this piece inside can be written as u to the minus 1/2. 1/2 is the square root, minus comes from the denominator. Integrating that gives you minus 1/2 plus 1 becomes 1/2 divided by 1/2. Instead of plus c, I have a bar, 9,409. The classical mistake on a test was to go back from u to x right now. No, that's why you did work for the 9 and 409. If 9 and 409 are already in terms of u, you plug them in, top minus the bottom. If you kept the previous limits of integration, then you have to go back. The answer should be a number. How you got this number, nobody cares. So just make sure it's correct and careful. 1/2 gets flipped, so it's going to be 2 over 8, brackets. U is 409, the square root, minus 9, the square root, because 1/2 is the square root. That becomes 1/4, square root of 409, no idea, minus 3. This is the final answer. The answer for the definite integral is a number. So I never had to go back to the previous variable. Does it make sense? So let's quickly practice. What do you think about this? What do you think about this file? So we have exam reviews as always. Actually, I don't have to go here. ASU MAT 266. I did attach it to the modules, but I always find it here when students ask. Final exam review. Here you go. So let's practice. What do you think? That'd be nice. If I take a screenshot, you have to be good at just identifying what your U should be. So for the first one we just did, u was ln x, because then du is 1 over x dx, and it was there. The second one is, if you don't see, integral sine of 4 pi t. What is your u? 4 pi t. Du then is 4 pi dx. Or you use a shortcut. The shortcut gives you integral of sine. You first think about that. Integral of sine is cosine or minus cosine? You have to ask, derivative of cosine is plus sine or minus sine? Minus. That's how I know. I always know only derivative, and then you always check. That's how I know it's minus cosine. Copy the piece inside and divide by the leading coefficient. That is a shortcut for u-substitution I taught you. You don't have to know it. You can just perform the whole thing. Can you see it, or it's too small? People at the back specifically. Now, how about the third one? X sine x squared. What is u? X squared. Usually whatever is inside is your u, because u-substitution undoes chain rule, and chain rule is something inside. It's a chain function or a nesting function. Function inside of the function. Yes? Oh, you're right. Yeah. Thank you. I don't know why I copied twice. Good catch. See? People paying attention. That's nice. X squared is u. Du is 2x dx. Continue. So it's going to be integral sine u over 2. And an integral of sine, you know it's minus cosine. How about number 3? Arctangent of 3x all over 1 plus 9x squared. What is your u? Derivative of some kind of function should give you another function. So arctan, if you differentiate, arctan is 1 over 1 plus input squared. If arctan of 3x is your u, then du will be 1 over 1 plus input squared. Calculus 1, remember, review that. That is 3x squared dx. And it's exactly what we have here. So actually the integral, which looks so horrible, is actually integral of u du. It's just u du. So the answer will be u squared over 2, which is arctangent square, over 2 with some kind of stuff. Do you know what's missing? Times derivative of the function inside, so times 3. I was wondering if anyone noticed. Chain rule says multiply. So you first differentiate arctan, but then times the derivative of the function inside. That is 3. Those are small things, they're not to forget. Now we just did number 5, u, but I changed it a little bit. 9 plus 4x is u. From here you solve for x and plug it into the numerator, and it becomes 2 fractions, and you break into 2 fractions. I don't want to do this one. The idea here is square root of stuff. You don't like it, that stuff conveniently should be u. Then it will be square root of u at least. And the last one, the same thing. I don't like having square root of x minus 9, so why not to make u as x minus 9 and see where it takes me. So then at least it will be square root of u, and then we're going to figure out the rest. How about this function? Temperature in Fahrenheit is 50 plus 13 sine pi t over 12. We want to integrate that. Do you know the integral right away? The integral will be 50, what did you say? 50t, I heard you. Plus or minus, what's integral of sine? Minus 13 cosine. Copy the function pi t over 12. And then what? Times 1 over pi over 12, yes. I would divide by the leading coefficient of whatever is inside. I cannot move, I think. Oh, I can. 12. That is the answer right away. But then they ask you to plug some numbers. Temperature, if T is in minutes, I don't actually know, in hours. then say from noon to 3 p.m. Then you plug from 0 to 3, or whatever it is. The point is to know how to do u-sub. And then these things you'll be practicing in your physics and engineering classes quite a lot, and chemistry. All those reactions, most of them have u-substitution. Is this good enough, u-sub? U-sub mostly is practice. Honestly, I can show you as many as you want, but you're not going to get better by watching me doing it. It's like showing you how to do push-ups correctly. I can show you push-ups like twice, 3 times, and 5 times, and 10 times. But then you just watched me. Did you get stronger? No. So you have to just go and do this. It's pretty annoying, but you have to do it yourself. Yes?
For number 5, you just set it equal to 0.
For number 5, no, you actually solve for x in terms of u. So x will be u minus 9 over 4. And then you're going to plug that into the numerator, blah, blah, blah. It's not classical u-substitution method. Usually I don't put this on a test. People get confused with fractions, and I don't want to check your knowledge of fractions. So that is just annoying. But it's nice to practice at home. Okay, good. That's for now is good for u-substitution review.